All right. Thank you so much for the intro. So I will be talking about a systematic approach for building full spectrum model monitoring. And as it was mentioned, my name is Mihir, and I am a product manager at Lyft on the machine learning platform team. So the machine learning platform team at Lyft is responsible for all stages of the ML modeling pipeline, from data discovery, training, feature engineering, to model monitoring and serving. So I will be focusing on the model monitoring aspect and how we build our model monitoring stack. So more specifically, I'll talk about three things. The model monitoring challenges we faced, what was the motivation for building a full spectrum model monitoring system. I'll talk about a deep dive into our model monitoring suite. So this would be a little bit technical on how we build and exactly what we build. And finally, I'll share some of the wins and learnings. These are the success stories from building and rolling out our system, and these can be applied to your organizations as well. All right, so before we get started, I wanted to talk a little bit about Lyft and machine learning models at Lyft. So some of you might not be familiar with Lyft because it's a North American company primarily, and we are a transportation network. So it's everything from ride sharing to bikes and scooters to transit to rentals. And we make a lot of decisions with machine learning models. So the key things here that are different from other companies' machine learning models are that these models are making very high stakes decisions because these are very real world interactions that riders or drivers or riders of transit, bikes and scooters are going to impact it by. So just to give you a few examples, we have ML models that do price optimization. So these are high stakes because these affect how much someone is going to pay for a ride and how much someone's going to earn. So ML models look at the real-time supply demand and optimize the prices. Another key set of models are safety models, where we try to identify if a given ride had a safety issue. So this is again very important to correctly identify with machine learning. If there was things like sexual assault or any bad things happening on our platform. There's ETAs. These are important for our business. So we have to correctly predict the estimated time of arrival for both your pickup time as well as your drop-off time. So these are important for riders or drivers because as a rider, you wouldn't want to know the correct ETA for example, for taking a flight. You wouldn't want an incorrect prediction. And for a driver, you want to know how much time you spend in picking up and dropping off someone. Finally, we have fraud detection models, which identify bad actors on our platform. So for example, one of the fraud cases is identity frauds. So if one approved driver gives their account to someone else and that person is not approved and they can just start using another person's car to drive, that could be a potential fraud, and we have to detect those kind of things. And we also have incentives models. So these models affect things such as coupons. Who do we give coupons or bonuses to? And this is impactful because these models are controlling hundreds of millions of dollars to incentivize riders or drivers to take different actions to have an efficient marketplace. So as you can see, a lot of these models at Lyft are making lots of high stakes decisions. On the other hand, we saw a lot of degradation in models, and I want to just talk about a few root causes of model performance degradation. So there's a gradual decrease because of diverse root causes, which include bugs in caller service. So this is the most basic example of how a model can degrade. It's if a caller service is using incorrect units. For example, if a service has a unit change from meters to feet, it's gonna just give garbage in and get garbage out. So this is a very classic example of ML models failing when there's an upstream failure. The second one is if there's a upstream data pipeline change. So for example, if a data pipeline schedule changes, a feature could be more delayed, which would affect model performance. Another example is a covariate shift. So this is when the distribution of input features changes. So we're going from simplest to like really complex issues. So covariate shift is somewhere in the middle. This is when the feature distribution changes. So for example, if Lyft launches an ad campaign, which increases the college student riders, so we're like campaigning to college students, this would change the distribution of the drop-off location, which might be consumed by a lot of other models. So the training and serving, there would be a skew because there's a covariate shift. Then there's label shift. This is the other side of it. If there's distribution change in the output labels. So for example, if there's a gas price increase, which there has been lately, which causes people to take more public transit, then a model that predicts the distributions for if someone drives to work or takes a bus to work might get affected because just the labels are getting affected. So none of the features are being affected, but the labels themselves, which is drive to work and bus to work, are being affected by some underlying factor that's not captured. And finally, a very complex to figure out issue is a concept drift, which is a conditional distribution change for an output given an input. So an example here would be the string driver was not wearing a mask and coughing. So this should not be classified as a safety issue in 2019, but it should be classified as safety in 2021 because of COVID. And as Lyft, we want to figure out if someone's not wearing a mask and driving, because in 2021 we had that policy. And so here the conditional distribution of which string should be safety and which should not be safety, that has changed. And if you do not retrain your models or don't have the new data, then the classification is going to be wrong because of concept drift. So as you can see from a bunch of these root causes, that these are a lot harder to detect than deterministic system errors. So for normal software, which is not machine learning based, you would have bunch of error logs if something goes wrong, and then you'd have thresholds which alert at different levels for those logs. But here, there's a very gradual increase, and it's not really very obvious when that starts happening. And so these are some of the, we observed some of these things with our models. And so now that sort of comes to this question of why monitor ML models. So we have all of these very important high stakes decisions being made by ML models. And then we also have these set of root causes, which I just mentioned. And as some of you might have heard of Murphy's law, that anything that can go wrong will go wrong. And so we did see some of these things affecting a few of our models. And this was the primary motivation for thinking about model monitoring. So this is a very concrete example. In 2020, we updated our ETA models to be more accurate for in response to declined demand due to COVID. So when COVID started, a lot of people obviously stopped going out and taking Lyft. And so we had to retrain our models. And we had to do that too, because the ETA models were over predicting without this retraining. However, when we did this, this caused other models to dramatically underpredict on pricing, which resulted in lost opportunity cost. So because a lot of these models are interconnected, fixing one model can deteriorate another model, and you wouldn't really know until like a lot of opportunity cost or something bad happens. So this was a motivating, this is the complex issue, like underlying distributions changed and then one model was retrained, and that affected another model. So here's where we were at in 2019. Monitoring models was very siloed by teams. Like some teams did it, some teams did not. There were one-off custom model monitoring solutions. So some teams would use mode reports, which is a third-party tool that we use. Some teams would just try to monitor using Jupyter notebooks, just one-off whenever they need. Some teams would try to use stats or alerts to monitor their models. But as you can see, like there were just a bunch of different tools that every team would use. So this was akin to building dams on tributaries. So tributaries being the ML models, and people would build these dams for their own use case. And as a platform team, we wanted to do much better because there was repeated effort, there was no centralized visibility, and these dams or model monitoring solutions were just not powerful enough. So we faced a bunch of challenges when we started thinking about building a model monitoring system. So the first challenges was how do we prioritize? There's so many things that you can build in this space. So for example, model type, should we start with online models, offline models? Do we monitor features or predictions? Should we do monitoring during training, real-time inference, or on a schedule post-inference? Do we sample single inference or on a or time series? So ideally, we just do all of these, right? But as a resource-constrained engineering team, like there's always lots of problems and like lots of solutions. You can't just build all of them. So we had to prioritize in a way that was most impactful. The second challenge was lack of standardization. So there were already a few one-off custom monitoring solutions, and we wanted to move them to like a standard solution. So to do that, you have to see what everyone else is doing and then incorporate that into the central solution, which is a challenge. There's technical challenges. So some teams had tight latency requirements or long delays in getting ground truth. And we had to build in a way that let ML modelers at Lyft configure and fine-tune the alarms. And finally, we had a bunch of adoption challenges once we built the system. So this is getting all ML modelers at Lyft to effectively use the suite of approaches in our system. So lots of challenges, both organizational, technical, and prioritization challenges. So we needed a strategy with which we could deliver an impactful monitoring system, with which we could address all of these challenges. So here's an analogy for our strategy. We wanted to go from minor dams and tributaries, which is one-off monitoring on models, to this kind of a comprehensive dam at the source. So this is a flexible, powerful, and in the future customizable, because you can build add-on things to your dam, and this gives you great visibility at the source. So this was our strategy, but you can't just build a dam in one go. So you have to do it in phases. And so we had a two-phased approach, where the first phase would be building monitoring techniques that are fast to onboard, but catch the most obvious model problems. So we wanted to have like good, impactful wins, which did not take too much time in onboarding the hundreds of models that we have. So that was the first phase. And in the second phase, we wanted to focus on the more powerful monitoring techniques for detecting complex problems. So complex problems being some of the distribution changes that can affect model performance. So this was our systematic approach for building full spectrum model monitoring. We had a trade-off between power and agility and simplicity. So on the bottom are our fastest model monitoring techniques, and I'll go into detail for each one of them. So model score monitoring and feature validation, these we built in the first phase. And these happen online. So this is online computation. And then feature anomaly detection, prediction anomaly detection, and performance drift detection were our second phase techniques. These are much more powerful and have and happen offline. So as you can see, this is a full spectrum, and there's in fact even more beyond these techniques that you can build. But this was a great starting point for us to have power and simplicity, and also build it in phases. So now I'll do a deep dive into each of these techniques. And also feel free to just ask any questions in the channel, and I'll keep taking a look. All right, so the first technique that we had, this is our most agile technique, and it catches the most obvious model problems, is model score monitoring. So this is an online, this happens online. It's a time series check on model scores. So for example, these are checks that models are not stuck emitting the same score over a period of time. So if that happens, so say your model scores are just um, always predicting 2 2 2 2 for an extended period of time, that means that there's might be an upstream failure, which is giving the same inputs, or your model is corrupted somehow, and it's just always predicting the same value. So simple statistical checks on a real-time time series is model score monitoring. And the way we do this is we look at the prediction scores from our serving system. It's called Lyft Learn Serving. And this is, you can just think of these as microservices that have all of the machine learning infra components, and they're used by hundreds of different models at Lyft. And they log prediction scores and a lot of other things, features, predictions into a central system. So we could build a time series computation on each of the prediction score time series. And if there's an alert, we can just page that team. So the benefit here is that there's no input from the user. So we could just auto onboard everyone. We can just look at the metric store, see what metrics are emitted, and just auto onboard. So it's very simple. You don't have to do anything to start using model score monitoring. On the flip side, the drawback is that there's this is a very shallow way of monitoring. There's no ground truth, and so you can't really catch any complex issues. So it's very simple statistical checks. There's no complicated computation on any of these. The next monitoring technique that we built was feature validation. So feature validation is a way to validate every single feature for every model scoring request against a set of expectations provided by the model owner. So an expectation is what you would want or want your features to be. So these could be range checks, type checks, set checks, and table expectations. For example, here the features are distance, city, and ride type. So the distance is -10. That's what a caller service is giving to Lyft Learn Serving. And the machine learning modeler could specify an expectation that distance should always be positive, and if it's not, then we would alert the user. So as you can see, the red boxes there, those are the inputs from users. So this needs users to give us some input for this feature validation to work. And the inputs here are profiled training data and the expectation suite, JSON. So the expectation suite would be expectations for every single feature, that this feature has to be in this range, this is the type of this feature, this is the set membership. And then once you have the expectation suite, you have to register it into our store, expectation suite store. And then for every inference request, we check all the features against all the expectations, and we page if any expectation is not met. Another key point here is that we built this this feature validation on top of an open source library called Great Expectations, which is a great library. It provides a really easy interface for setting expectations. So I'll show you an example here. So you could, to set the column, to set an expectation that a column should not be null, you can say suite.expect column values not to be null. And you can set the severity that if it is null, then this should be an alert. You can have set membership, so ride type should be regular or shared or XL. And then you can have range column values to be between, and this is a range check, so distance has to be between 0 and 100 miles, and we also have conditional checks there. So that means if distance is not none, then it should be within this range. So very easy to set up. Like a domain expert would know what features they're expecting. So we do need input from the user. We also built a custom model monitoring library, and we on top of Great Expectations. And we did this for a few reasons. One was we wanted to include conditional expectation support. So in the last example in the snippet above, there's a condition provided. And we have a lot of use cases where a feature is fine to be none, but if it's not none, then it should be within a certain range. And we have a bunch of these similar use cases where if a condition is met, then another condition should be met. We also built a data profiler geared towards online feature expectations. We built an abstraction that allows for changing to a different data validation library. So we didn't want to be locked into Great Expectations. It's an open source library, as I mentioned, but open source libraries can stagnate or just not be updated. So we wanted to have an abstraction that allowed us to change the underlying validation library. And in our model monitoring library, we also built integration into Lyft's infrastructure. So this is our logs and metrics. We wanted to have a system which was compatible with the way in which we log and emit metrics. So we did this at the monitoring library layer. And finally, we had to build a low latency data validator. And the reason for this is that Great Expectations typically operates on larger data sets, but we wanted to do this at every inference level. So we had to have a much more lightweight data validator so that we didn't add too much latency on every request. So the benefits of feature validation are that it happens real time. On every single request, we can check if expectations are being met, and we can alert the user right then. On the flip side, this is again not very powerful because you cannot catch complex issues. Like all of your features could be meeting expectations of that you set, but if the underlying distributions of the labels or the features are changing, then you would not be able to catch that. So now we're getting into the more offline computation, and these are more compute heavy techniques, and they happen on a schedule. So these checks are a lot more powerful and have to happen on a offline schedule for it to work. And so the first one is anomaly detection. So this is fully automated statistical checks for feature and model score time series data. So as I mentioned before, Lyft learns serving logs all the predictions into our database. So we can build anomaly detection by just looking at the log store. So for each model, we look at the features and the predictions, and we compute the feature statistics and the prediction statistics and run anomaly detection checks. And we can then present for each model, we can build a dashboard and present all the anomaly detection, whether it's a feature anomaly, volume anomaly, prediction anomaly, or some other anomaly. And users can take a look at this dashboard to figure out if there's any anomaly. And another key thing to mention here is that there's no user input needed for anomaly detection because we're just looking at the log store and computing these metrics without needing any configuration. So in our experience, the most on the left hand side is the dashboard. This is what a machine learning modeler would see. They could see the feature null percentage and what the z-score is. So if a z-score is over 2, that means that it might be an anomaly. So in our experience, the most indicative signals for potential problems are z-scores of over 2 for call volume, model score, a mean feature value mean or feature null percentage. So these were the most indicative. The benefit here, as I mentioned, is that there's no user input needed for creating anomaly detection, because we're just looking at prediction logs and auto onboarding as many models as we can. The drawback is that this technique can be a little too noisy, because sometimes the anomalies are expected. So for example, if there's a feature called ride intents, which looks at the number of people requesting a ride, that feature can be anomalous on, for example, New Year's Eve or Halloween. And a bunch of other features could be anomalous in a given geographic area. If there's an event, or like a sports event or concert, some anomalies are expected. So z-scores over 2 or even other statistical checks would just give a lot of false positives. So that's the reason why in the previous diagram we did not have our anomaly detection system connected to our paging system, because this would give too many alarms. So what we have here is a more pull-based approach for users. So users can just go to this dashboard and check the anomalies within the past week, and see if there was anything bad. And if some teams want to have this integrated with their paging system, they could do a little bit more work and look at our anomaly detection database and just page themselves. But by default, we just provide a dashboard. All right, so this is the most powerful technique and also the most involved from a ML modeler's perspective. It's called performance drift detection. And this is model performance evaluation based on user-defined metrics, typically by processing a model score with ground truth data. So these metrics are, these are looking at ground truth, and we need a bunch of inputs from the user for this one. So the first input is the metrics query. So how do you get the metrics from Lyft's databases is one thing that we want to get from users. The second is the validation rule, which is when should the alerts fire. And these are inputs that a user with domain knowledge would have to give to our configuration system. And once we have these pieces of information, we can join the metrics, join the model score with the ground truth data, and then run a metrics compute, and then run the validation rules on those things, and alert the user if the paging fails. So this is actually a lot of computation, because for each model, we'd have to query the ground truth, join it with the model score, run validation checks on it, and send it to the dashboards as well as the paging system. So the way we built this is using distributed computing. We have this environment called Lyft Distributed, which is powered by Kubernetes, Spark, and Fugue. So we have a pretty good blog post about this on our blog on just how the distributed computing works. So you should check it out if you're more interested in the details. But yeah, so this is the most powerful. You could catch lots of different complex issues. Concept drift, label drift could be caught if you have the right ground truth and you join it with your model scores. So to show you a more deeper dive into how this works is we have these configurations that a user would have to put in our performance drift detection workflows repository. So a user can specify 71 supported statistical metrics. So these are the sklearn metrics. They could just say that in their query, this is the true column and this is the predicted column, and then just specify which processor they want to use, and then we would run all of those post processing to get the metrics. On the other hand, some users might have custom metrics. So within the SQL, they could just define another column that gives that specific metric. So we provide both flexibility here as well as ease of use by having sklearn metrics. And this is how a user would consume performance drift detection. So they could view the metrics over time. So on the left hand side, you can see that there's a bunch of metrics, and you can see the average value of that metric for each date. And on the right hand side, we also have monthly comparison for metrics. So this is month over month or week over week. How is your metric doing? So the lighter the color, um, the older it is. So the frac time mean error, as you can see, 4 weeks ago was much higher than like the darkest one, which is lower. So in these views, we give machine learning modelers a very intuitive and easy to understand, uh, easy to use way of seeing their metrics over time, comparing how their model is doing. And they can keep adding more metrics, and we just automatically surface them into these dashboards. All right, so I'll take a second and see if there's any questions at this point. Um, Also, feel free to speak up if you're on the um, yeah, on this webinar. Just feel free to speak up, and I can answer any questions. There's quite a bit more, but just taking a second to stop for any questions. Okay, so question for the first metric. What is the metric 2231 in this case? Since there is no ground truth, what are you measuring against? So these, yeah, this is the predictions. So here, these are just what, so for example, if there's an ETA model and it's just stuck predicting like 5 minutes, 5 minutes, 5 minutes, 5 minutes, then we would say, okay, like this model is stuck. Are these, so this is not checking any ground truth. This is just the prediction value. Or if a model is always predicting off the one class. So if it's a cats versus dogs classifier and it's always just predicting dogs for like an hour, then we can say that there is some problem. Could you explain more automated statistical checks? So what are your statistical checks? So these statistical checks are, as I mentioned, z-score is one of the statistical checks. So we can look at the feature distributions, and look at the feature values and see what's the z-score of the distribution. We also have other things that we are going to add, such as the KS score. So this is an extensible system, anomaly detection, and we will be adding more statistical checks as needed. But as I mentioned, these ones tend to be more, they have more false positives. So by adding more statistical checks, you might not add more value, um, unless you have a good solution for reducing false positives as well. So will slides be shared? Yes, I will share the slides after the talk. We also have a very recently published blog post that talks about this content. So you do offline anomaly detection and use that as a trigger to train a new model, collect new data. So not necessarily to trigger a new model. So we do have a separate system for model CI/CD, which someone has to configure to retrain models. We don't automatically retrain based on an anomaly, because as I said, sometimes anomalies are expected, and not every anomaly necessarily means that you need a model retrain. This is more to inform a machine learning modeler that you need to like retrain or get new data, or this model is just broken. So but yes, we do provide, if a team wants to retrain based on anomalies, they could do a little bit of engineering work to hook it up with our model CI/CD system. So that's our continuous integration and continuous deployment system. So they could hook up anomalies or performance drift to trigger a model retrain, but we don't provide that out of the box. All right, so yeah, just keep posting your questions. I'll proceed, and then I'll have a few minutes at the end to answer those questions. All right, so we built all of these great tools. We built lots of monitoring techniques, but building great tools is only half the story. If you build good tools, that doesn't mean that everyone just starts using those tools. For most data scientists, who are the people who build these machine learning models, operational concerns of running their models in production are typically not top of mind. And the reason for this is that we have lots of big modeling problems, and data scientists typically want to go and solve the next big problem to land the most impact. And sometimes it's just harder to rationalize looking at the models that you've already shipped. So if we build this monitoring solution, and a data scientist is looking at whether they want to build a next new model or just monitor something they built a year ago, they might just gravitate more towards building a new model. But as a platform team, we do want people to use these tools that we built. And as I mentioned, we have some onboarding steps. So we want every modeler at Lyft, and we have about 300 people who are working on machine learning models to use these tools. And so we started by looking at the model monitoring usage funnel. We initially, when we launched this, we saw little organic adoption, so we had to really inform people that they should be doing this. So we saw that there were these 4 stages of whether someone's going to use or not use model monitoring systems that we built. First was awareness. Do they even know that we have this system built? Second was, do they know but don't understand the value of it? Maybe they think that once they ship their models, it's they don't need to really monitor it. So value proposition was another step in the funnel. After value proposition is onboarding. So of the people who understand that model monitoring is very important, can they easily onboard to the system? And then finally, once they onboard to the system, can they use it? And by use, I mean look at the alerts and the dashboards and take the right actions to avoid problems with models. So that's the final step of the funnel. So we wanted to increase, accelerate every single part of the funnel so that people would use the system more. So we did a bunch of things. So here's a list of different actions we took for increasing awareness, value proposition, onboarding, and usage. So we had lots of communications, both synchronous and asynchronous, which means emails, Slack messages, brown bags, internal brown bags. We did personalized pitches to some of the main teams that we thought should be using it. We personalized our pitches to them, and we said, hey, like, you should just spend a week and onboard to all of these systems because it would be very valuable for the company and for your team. Finally, we had some case studies to really show the impact of model monitoring, like the few problems that were caught. We highlighted them and said, hey, like this many millions of dollars could be saved if there was model monitoring present. So we had a couple of those case studies that we shared widely. Making mandatory was one of the most impactful things we did. We said that for every model going forward, you would have to have model monitoring. We did this for feature validation and performance drift detection. And we said that we as a platform team think that this is very important to the business and it's a best practice. So we are going to just have programmatic checks before you could deploy your models. So you have to pass model monitoring before any new deployment. For increasing onboarding or increasing the velocity of onboarding, we automatically onboarded a lot of models for feature validation by profiling data. So we looked at the features and we saw we inferred types and ranges and just automatically generated the expectation suites, and then users can go and tweak it. We had lots of proactive onboarding sessions, so that just means we assigned engineers on our team to go to a team and just help them onboard. We try to really improve the user experience, so just better documentation, reducing the number of steps. And for increasing the usage, which is really fixing the problems, we handed off all the pagerduty alerts to all the teams. So initially, we were getting all the alerts as the platform team, but we had a strategy to hand it off once our system was reliable enough. And then for anomaly detection, we didn't really have alerts, so we started tracking use cases and assigning tasks to teams. So whenever we saw that, hey, there's an anomaly in this model and it has not been observed by a team, we would just create a ticket and assign it to the team. And we've been really actively involved and getting inputs from all the people who use our system to understand their unmet needs and build it. And then the next thing that we're doing with the system is giving a biweekly alerts summary to users. So we'll send an email and say, hey, these were the alerts with all of the models that your team owns, and here's how you should fix them. And this is just more proactively giving a summarized view, and this would go to even managers or execs could see the state of different models and how modeling happens at Lyft. So now I'll share some of the wins and learnings of building the system. A question that we get a lot is, why did you build instead of buy? And the reasons are simple. We had 5 reasons actually. Monitoring models was high urgency and high impact for us. So as I mentioned in the beginning, ML models make lots of high stakes decisions at Lyft. And so this was like just very urgent for us to do and impactful, because degradation in these very important models, it can be very adverse to our business. Secondly, in early 2020, there weren't great third-party solutions available that met all of our needs. So there were a few, but they weren't as robust and with all the features that we wanted. We also wanted to build a deep integration with all of our other tooling. So as I mentioned, we have these programmatic checks where with our serving system, with which we can just prohibit model deployment unless there is monitoring. And also we wanted other seamless integrations into our training system. So all of that was very easy to do if we would just build. Building also enables customizations. So if another team wants a new feature, we can just add it whenever, instead of having to request it through a third-party vendor and not knowing when we'll get that feature. And we also just wanted to avoid a vendor lock-in for this very important part of our ML ecosystem. So these were the primary reasons why we decided to build instead of buy. For other organizations, it might make sense to buy if your ML models are not really making very major decisions, and you don't have the engineering bandwidth, or you just want to use something off the shelf, don't have time, but still want to monitor, it might make sense to just buy a solution. And I'll use the dam analogy here. We wanted a seamless integration. That's the key point why we decided to build. So here the dam is the monitoring system, full spectrum monitoring system that we just talked about. Our serving system is like really well integrated with our monitoring system. As you can see in this Hoover Dam photo, the serving system just goes through the monitoring system and then it's able to serve. And that's exactly how our monitoring system works. And then we also have, we can build very easy customizations. So if some team wants, in the future, has a very special case for building for some type of monitoring, we can very easily have this customization. So here the customization is a power plant on the dam. So we can also have a similar customization easily built.